Hi class, so today we're going to discuss the pH scale. A pH scale may be something that you have been familiar with or maybe not. Excuse me. Last section we discussed concentration in molarity for hydronium ions and hydroxide ions. And now we're going to look at it in terms of a pH. A pH relates to the hydronium concentration of a solution. So we focus on the hydroniums and that will give us the pH for this, for whatever we're looking at. So let's look at a pH scale. A pH scale, where you can see is red, is acidic conditions. Neutral is in the middle at 7, and then basic is blue. Now, the stronger an acid is, the closer to 0 it is. As it increases, it goes to neutral and then to basic. So if you're looking for a strong acid, you want the pH as close to 0 as possible. For instance, gastric juice is 1.6. It's a very, very strong acidic that is in your stomach. So what we're going to look at is actually understanding pH numbers. On a pH scale, 7 is neutral. Anything above 7, meaning going to 14, even though the scale on here is pointing down, is let me say a larger number than 7 is basic. And anything below 7, a smaller number than 7, is acidic. So the pH scale is used to indicate the acidity of a solution because we'll go by the pH. What's the pH of this? If it's below 7, it's acidic. It could be very strong acidic or slightly acidic. And if it's 7, then it's neutral. And if it's above 7, larger than 7, then it's considered basic all the way to strongly basic. So the hydroxide concentration, which is what we looked at the last section, hydronium concentration, is for an acidic solution is stronger than the 1.0 times 10 to the negative 7 molarity. It's neutral if it equals, and if it's lower than the less than the 1.0 times 10 to 7 negative 7 molarity. I'm getting so tongue-tied. Okay, so how do we determine the pH? Well, you can use a pH meter, and what you do is you clean this probe, and then with DI water, and then you stick into solution. You set it for 25 degrees Celsius because that's what these pHs are set at, and then it'll tell you the pH concentration. For this one, it's 4.0, which means it's acidic. You can even see right here. You can use pH paper, which I've used many times. I've used both of these many times in the lab, and the pH paper you stick it into the solution, and the color will change to whatever pH it's at. So it can go all the way to very blue, almost black, to very pink. So this one, you would hold this up to this. This is your, what do you call it? This is what you compare it to. And you'll hold it up, and then you can determine what the color is. Or you can have a color indicator. There's a titration. Had we been physically in lab, you would have did a titration, and that's a color indicator. And indicators, the colors will change based on the pH, very similar to pH paper. So this last titration that you'll do in lab, you would have had a clear acidic solution, and the indicator phenolphthalein is clear in acidic solutions. But as it gets to a pH above 7, close to 8, it turns pink, it turns pale pink, and then as you increase, it turns to very dark pink. So it changes color when it hits the correct pH that you want. It's very sensitive though. Most students hate titrations because it takes a lot of patience, and what I have found, unfortunately, a lot of students don't have patience in chemistry class, not labs. It's very, very sensitive. So let's take a look. Last section we discussed the water dissociation and how it affects the hydronium ion concentration and the hydroxide ion concentration. Now we're going to determine based on these values if something's acidic, basic, or neutral. So we have hydrochloric acid with a pH of 1.5. That is below 7, so it is acidic. B, pancreatic fluid, the concentration is 1.8 times 10 to the 8 molar. I'm going to tell you right offhand, this is, what do you think it would be? Well, we could look here, and we have something very similar right here. It's basic. Why is it basic? Because we only have out of 14. So if this is 8, this has got to be 6, which means that this has a larger value than the hydronium concentration. So it's going to be basic. Sprite soft drink is a pH of 3.0. So now you can all feel good when you guys drink a soda. About your teeth been wearing down. I'm no better. I went my whole life never drinking soda, and then all of a sudden now I got married and all I drink is Dr. Pepper. It's horrible. I worked in hamburger stand. I wouldn't touch soda. I was so tired of seeing it all the time. Anyways, in high school. So 3.0, that is acidic. pH of 7, that is neutral. And then we have a hydroxide concentration of 3 times 10 to the negative 10. So we have something similar right here. Now, if it's out of 14, then that means that the whatever makes it up has to be stronger, has to have less zeros if you get confused. The smaller the negative number, that is what the conditions are. So in this case, if this is 10, this has got to be, the hydronium ion concentration has got to be acidic because it's got to have a negative 4. And here, the hydronium concentration is negative 12, which means that the basic, let's see, we have it here, it's reversed, but then that means the hydroxide concentration would be a negative 2. This makes it basic. And let's see if I'm right. Acidic, yes. Basic, yes. Soft drink, acidic. Neutral, acidic, and basic. So, and this one's acidic because remember, we're looking at hydroxide ions here. This one's the hydronium ions. Okay, so now we're going to go and jump in between the concentrations and the pH. And you have to know how to do this on a calculator. Everybody has different calculators. This is a picture of it's my calculator, but I did not take this picture. I found it on the web. I don't even know if that's actually, does that say something? I hope not. And if it does, I apologize because I really didn't look at it. Okay, so I was looking at the buttons. The pH scale is a logarithmic scale that corresponds to the concentration of hydronium ions on aqueous solution. So we're dealing with the base of 10. This is very similar to, there's not, if you see a pH that's 4 and a pH that's 5, there's a huge difference in between. It's not just a very small number. It's the same as if you understand how they measure earthquakes. Jumping from a pH, an earthquake that's a 3 to a 4 is vastly different. It's huge. And that's the same thing with pH. So don't get caught up on all that. Just understand how to do the calculations. To calculate the pH, the negative powers of 10 in the molar concentrations are converted to positive numbers. So if the hydronium concentration is 1.0 times 10 to the negative 2, you're going to plug it in. So here we have a pH. We have a negative log, and then you enter the number in. So for me, I would hit negative log, and then I would enter in whatever the number is. I would enter this number, and then I would close it with the parentheses, because the minute I do a log, it enters a parentheses. And then it will give me a 2. Now, beware sig fig numbers. It's only going to show me a 2. It's not going to show me this outer part, and you guys are responsible for keeping sig figs. And we're going to cover sig figs on this later. So if you get just a 2, you need to count and look at what you're dealing with in order to determine what the sig figs are. And this, I will be honest with you, can be slightly confusing. It's not as easy as, I shouldn't say easy because I think most of you struggle with sig figs. Well, let's just put it this way. Chemistry aside made it a little harder for you. Okay, so now let's take a look at sig figs. So to determine the sig fig values in a pH, the number of, I'm just going to read this straight off and then explain. The number of decimal places in the pH value is the same as the number of significant figures in the coefficient of the concentration of hydronium ions. This is where I'm telling you to be careful with your values, because you may be given just a numerical value of 2 when you actually need 3 sig figs. And then you're going to add some zeros. The number to the left of the decimal point in the pH value is the power of 10. Let me explain it. I think it might be, okay. So what this means is that if you're given this value here, you have 2 sig figs. And then this is the pH. So to make it easy on yourself, look at this and count. 1, 2, 3. You should have 3 sig figs if you're trying to make it as simplistic as possible and not trying to break any of this down. 1, 2, 3. If you're trying to fully understand this, let me explain. You have a negative 2 here. We're not looking at the negative number. We're only looking at this number right here. We're going to take that, and that whatever number, how many there is here, is in front of the decimal. Whatever is here is the coefficient. That's how many go after the decimal. Or you can do it my way. 1, 2, 3. 1, 2, 3. Whichever, as long as you understand, sometimes you can take shortcuts and be okay with it. But you need to understand why you're taking the shortcut. So let's take a look at these numbers here. So this is what I'm talking about. It's a log scale. So it's a base of 10, so it increases tenfold for this. If you don't understand what that means, look it up. I'm not going to go into this here. I'm just going to show you that a pH of 2, if you plug it in, which we're going to look at how to go from pHs here to get to these numbers. But this will show you 1, 2, 3. I'm going to show sig figs. 1, 2, 3. So a pH here is a 1.0 times 10 to negative 2. This is 10 to negative 3. This is 10 to negative 4. pH decreases as the hydronium concentration increases. So as these for here, we're actually increasing towards more neutral. If we go this way, we're actually increasing towards more strongly acidic conditions. The highest value for an acid is 0. All right, so now let's plug this in so you can understand how to do these in a problem. Aspirin, acetylsalicylic cyclic acid. I have learned to say it and then I mess myself up. Let's just jump in. If a solution of aspirin has a hydronium concentration of 1.7 times 10 to negative 3, what is the pH solution? So let's take a look at what we have. We are given the concentration, we need the pH, and we need the pH equation. So we're going to plug this in. So in order to get the pH, we're going to plug it in using the log. And here is my, again, I copied this over. I would do negative log, and then I would plug this in, and it would give me a value. Every calculator is different. This may be used for others. I don't have any of these function on my calculator, but so I'm showing you mine because mine's different than what this one's saying to do. Okay, so now we're given all these numbers, but remember that fun thing about sig figs? You need to make sure you remember how to do it. So here is the top part that we just did on the previous slide. Now, you can do it my way. 1, 2, 3. 1, 2, 3. Or you can make sure you fully understand this, which honestly you should know anyways, because if you get questions about this, I haven't done the homework yet, so I don't know what questions they may ask, but you definitely should know. This means that you have 2 sig figs in the coefficient that go after the decimal. And then this number is exact. It's whatever, how many values you have here, that's how many you're going to have here. So you take that answer, there's one decimal in front of the, one value in front of the decimal, that matches that, and you have 2 sig figs for here, so those are 2 sig figs, and there you go. Okay, so let's take a look at another problem. Find the pH of a solution with a hydronium concentration of 4.0 times 10 to negative 5. So we're given all our information that we need to solve the problem. Again, we're going to plug it in, and then we are going to determine what the answers are. So for me, I did this way, 1, 2, 3. So my answer should have 3 values. 1, 2, 3, and there it is. But remember, again, 2 after the decimal point, 1 for the exponent. So you definitely need to know why this is, but once you understand it, then you can do my little shortcut to not make it as difficult to understand. Okay, given the pH of a solution, now you can reverse the calculation to obtain the concentration. So let's say you were given the pH, but you need the hydronium concentration. We're going to go backwards now. So again, this is my calculator, and my calculator has a log. You see it has a little 10x here in yellow? So that's what you need in order, if you have a pH, you're going to use this one to do that, which is exactly what this one's saying here, that you have to use the second function key. So I would hit Shift, and then hit this, and it will show a 10 and a parentheses for whatever I need to plug in. So let's do that. Determine the hydronium concentration for a solution that has a pH of 3.42. So we're given all the information, we're given our formula, and the hardest thing, honestly, is to make sure you're doing it correctly on the calculator. So let me explain. When I did this on my calculator, I did not get this number. And I couldn't figure out why. I hit Shift, I hit this, and I entered 3.42. I was getting some weird number. Then it occurred to me I might need to use the negative to get this to work. And once I hit negative in it, it gave me the number, not in scientific notation, but in regular decimal form. And that's fine. You just got to make sure that you can see that. And then change it to scientific notation if that's what it needs to be. So for mine, I had to actually use a negative in order to get this to work, which it shows right there. On mine, I needed to plug that in. On some of these, they're not even showing it, or they're doing the plus and minus here. I honestly don't know how to do any of these with the different calculators, but the minus is showing here how to add that in. Okay, so I have 1, 2, 3. So that means I should have 2 sig figs here and 1 value there, and that's right. So if they're asking for 2 sig figs, it's going to be 2 sig figs on this one. And that's it.